Hello and welcome to the last lecture in our BQIT lecture series. Today we'll be talking about noise and quantum error correction. So the first topic is going to be noisy evolution. So as you know, the evolution of a quantum state may not always be perfect in real life scenarios, which is why implementing quantum computers is such a challenging task because of the noise of the surrounding environment introduces a loss of information in our quantum system. So there are three different types of noisy evolution that we're going to talk about today. The first is going to be noisy evolution from a random unitary. And the second is going to be the noisy evolution as the loss of a measurement outcome. And the third is going to be a noisy evolution from a unitary interaction. So, to start with noisy evolution from a random unitary, let's consider the following example of a bit flip channel in which a bit flip operator or a Pauli X matrix is applied to a state, quantum state psi with a probability of P. So in this case, we'll get an ensemble of these two possible states. And as we know from the previous lecture, this will constitute what's called a mixed state. And so since this is a mixed state, we can also represent this as a density operator as so. So we're going to define this as rho. So, and writing this out, we get this following expression for rho prime, which is the fixed state due to the noisy evolution of the bit flip channel. And if we assume that our initial state is a mixed state rho, we instead get this final state if we apply the bit flip channel on each of the states in the ensemble. So we can represent the effect of our bit flip channel as the following operator. So suppose instead of applying a Pauli X, we instead apply a random unitary, UK with a probability P of K. Then, as we've seen above, the final operation is going to be the weighted sum of the conjugation of rho according to UK. And so this is going to be our noise channel for a mixed state rho. So next, let's talk about the noise evolution as the loss of a measurement outcome. So recall from the last lecture, according to the measurement operator formalism, the probability of a measurement outcome, P of n, can be represented as the following expression using the measurement operators M of m. And also the post-measurement state, given that the outcome is in fact n, will be this projection of the initial state psi. So then, let's suppose we have an ensemble of states consisting of psi of x and p of x, and we perform a measurement with a set of these measurement operators, where the measurement operators, of course, by definition, they need to satisfy the completeness relation. So as a result, the final state will be this expression, as we'll prove in the next slide. So for our noisy evolution, we have our input ensemble and measurement operators. And of course, for a single state in the input ensemble psi of x, we have the probability of an outcome k given that the state is psi of x is going to be, of course, this expression. And this will also be the post-measurement state. So given these, we get a output ensemble consisting of these conditional probabilities, the joint probability of the state being in X, and the measurement outcome being K, and of course the post-measurement states. And through this ensemble, we can construct the post-measurement density operator as so. Clearing up some of the algebra, of course, and using the fact that this joint probability equals this expression according to the definition of the conditional probability, we get this final expression over here. And of course, since due to linear properties, we can rearrange this expression as so. And so we've seen that this expression over here is indeed rho, our original rho, before we measure it, and of course we get this expression over here. So moving on, let's talk about the noisy evolution from a unitary interaction. So let's suppose we have some system A, and this system is going to be interacting with an environment E. And so the joint composite system, we're going to represent as the tensor product between these two density operators. And suppose that the composite system undergoes some unitary interaction, some unitary transformation, which means that the state after its evolution is going to be this conjugate state. And so to obtain the final density operator of system A after this operation, we simply trace out, take the partial trace with respect to E to obtain the final subsystem density operator. Of course, as a caveat, of course, we can't, without loss of generality, we can instead use this pure state representation of rho E by doing what's called a purification procedure, in which we assume that there is another system called the reference state present, and we can represent this mixed state as instead the pure state, the partial trace of a pure state in the composite system E R. So working out the algebra, let psi ER equal this operation where 0 is the joint pure state between E and the reference system R. And then, of course, our sigma A can be represented as the partial trace with respect to E, and we substitute this expression over here. And moving the terms around, we obtain this final expression where we've also included the partial trace according to the reference system R. So, in light of this representation, of course, we can then represent the final system's sigma A as this expression over here. And so from this expression, we can further derive another relation. So from the definition of the partial trace, we simply sandwich this expression in between these two expressions and take the sum according to the index I. And applying this operation gives us this final state over here. And then we're going to define these operators as BI. And these are going to be what's called the Krauss operators of our evolution. And if we notice from the definition of our operators P of I, if we sum Krauss operators as so, we'll notice that doing the algebra, since this is the identity, this goes to the identity, we get the identity with respect to the system A, which means they also satisfy something that's called a completeness relation. And such operators, which represent noisy evolution from unitary interactions, they can be represented in terms of what's called a Krauss operator. So here are some examples of noise evolution. So recall from the last lecture, we could represent a density operator in terms of a Bloch sphere with a Bloch vector R that is less, whose size is less than or equal to 1. And so, for example, let's say we have the bit flip channel we mentioned earlier. Then using this representation, we can plug this representation into the bit flip channel, and we get this expression over here. So basically, using this density operator formalism with the Bloch sphere, we can basically model noisy evolutions as the modification of Bloch vectors. And so you'll notice that, for example, the dephasing channel or the bit flip channel, that the density operator's Bloch sphere vector sometimes shrinks in size, which obviously is a effect of the noisy evolution itself. So, and of course, if we have the bit flip channel, we also what's called the dephasing channel, which is where we apply the Pauli Z instead of the Pauli X here as well. And so we can generalize such channels to be in terms of what's called a Pauli channel. So instead of our density matrix is transformed by conjugating with an arbitrary Pauli matrix with a certain probability. And so the Pauli channel over here can be represented in general for the single qubit case as this expression, in which it's a weighted sum of the conjugation of our original density matrix with each of the Pauli matrices, the X, Y, Z, and also the identity matrix. And so in the Bloch sphere representation, it gives us this expression over here. So another type of channel is called the depolarizing channel. And so this transforms rho into 1 minus p rho at p of pi, where pi is a maximally mixed state. And this can be interpreted as a channel which transforms the original density matrix operator into the maximally mixed state, or the state which rho in the Bloch sphere representation, our Bloch sphere vector is 0 with a probability of p. And so in terms of Pauli matrices, it can be represented as the following. So using the fact that our maximally mixed state equals this expression over here, we can represent it as this expression over here, the depolarizing channel. So another example of a noisy evolution is the amplitude damping channel, which occurs in many different physical systems up to a first order approximation. So we have a ground state and an excited state, 0 and 1, and we have an example of a amplitude damping channel is spontaneous emission, which is a process that tends to decay the atom from its excited state to its ground state. So the Krauss operators A0 and A1 with a parameter gamma, which is between 0 and 1, this denotes the probability of decay. And this amplitude damping channel can be represented in terms of these operators defined as the following over here. And so, of course, you can do some algebra and check that this does, in fact, satisfy the completeness relation. So given the general form of a single qubit density operator over here, where eta, of course, is some complex number. This amplitude damping channel, of course, performs this operation. And if our rho is in this chart, in this form over here, we can do some algebra. So this is A0, this is A1. And then multiplying these expressions out and adding them, we get this final expression over here. And so if we were to keep repeating this expression, of course, these terms would be multiplied n times, and this would exponentially decay over here along with these terms. So as we see, the amplitude damping channel exponentially basically decays these two diagonal terms along with these diagonal terms as well. So the final example of our noisy evolution is what's called the erasure channel. So the erasure channel is can serve as a simplified model of photon loss in optical systems, and it's defined as the following. So it takes our rho and changes it into the sum of 1 minus some epsilon rho, add some epsilon multiplied by the projection to some other third state. So this would be a leakage state. So what the state is basically normally what we have as a qubit uses only two different states, but a leakage state would be some third state over here into which the system leaks unintentionally. So basically, it's the third state in what's called a Q-trit. But in this case, we don't usually intend for this third state to be used. And so the original information that's supposed to be stored into 0 or 1 state is instead erased into the third state. And most of the time, this third state might actually be have a lower energy. And sometimes by noise induces a transition to this third lower level, which erases any information that was stored in either the 0 or 1 states, which is why it's called an erasure channel. And so this erasure channel can be represented in terms of these Krauss operators. So moving on, we've seen how different forms of noisy evolution can occur in quantum systems. How do we deal with such noise? How do we correct errors? And so the main problem of implementing quantum computing is how to effectively perform what's called quantum error correction, which basically corrects the different forms of noisy evolutions in order to restore the information that was stored. So quantum error correction is actually inspired by classical error correction. So classical information on computers is also stored in different platforms, and errors do occur in the classical case as well. So for example, let's say we have a classical binary symmetric channel in which we either have an initial state of 0 or 1. And the effect of noise in this channel is to flip the bit being transmitted with a probability of p. So as you can see here, if we start with the 0 bit, there's a probability p of it being flipped into 1, and vice versa over here. So in classical error correction, what happens is that we try to protect the bit by actually copying it. So in this case, we've copied it 3 times, and we restore the information by what's called majority vote. So we use the fact that the probability of more and more bits being flipped is unlikely, and so we assume that the original bit is the majority bit, or basically the bit in which the majority of bits are in. So for the 3-bit error correction code case, if we had a transmission of 1 bit in this case, since there are 2 different 0 bits, we would assume that the original copy was 0, and then we would correct this bit by flipping it to restore its original state. And each of these different repeated bit strings are called logical zeros or logical ones. And so by indicating the logical adjectives, we're indicating that these are the basic error robust units of information that are stored. And so the reason why this approach works is because the error probability in which 2 bits are flipped or 3 bits are flipped in which we would make a mistake. So if we had 2 bits flipped instead, using majority vote, we would mistake this 0 to be the error, and so instead we would restore the state into the 1 state, which is incorrect. And that's called what's called a logical error. But the reason why this approach works is that the probability of a logical error occurring is sufficiently low. So whenever this inequality is satisfied, basically the probability of logical error being less than the probability of the physical error is when this error correcting code is practical, and this is when p is less than a half. So there is a quantum version of this bit flip code, and it is the case the majority of the time that certain quantum error correction procedures are inspired by classical error correction procedures. So the quantum version of this is the 3-qubit bit flip code. But before we can go into the details, there's some important differences between classical information and quantum information that need to be addressed before we start developing our own quantum error correction codes. The first is that there's no cloning available. So according to no cloning theorem, there isn't a unitary operation we can use to perfectly clone a quantum state. And second is that our errors are continuous because quantum states, unlike classical states, have superpositions. And these superpositions have amplitudes that are stored continuously, not digitally. And third, measuring our quantum state destroys the quantum information stored inside that state. And after such a measurement is performed, that information is irrecoverable. But fortunately, despite these caveats, none of these problems are fatal to quantum error correction. So let's look at recall taking a look at the 3-qubit bit flip code, the main error we want to correct is the error that's caused by the bit flip channel, which basically flips a bit or performs a Pauli X operation with a probability of p. So for a quantum state over here, recall that for a pure state over here, that's the probability p of being x of psi and a probability 1 minus p of being just psi. And so if we represent our state in general as in this form, if a bit flip were to occur, basically the amplitudes are switched. So we can construct an error correction code in the same manner as we constructed the classical 3-bit code by simply encoding our original state by repeating it basically a certain amount of times. And in this case, we're going to repeat it 3 times. So instead of 1 qubit, we'll use 3 qubits to represent 1 bit of information. And so we can convert our physical qubit into a logical qubit by just replacing each of these basis states with their corresponding logical basis states over here. And so once we've finished encoding the state, let's see how we perform recovery on this logical state. So let's suppose a bit flip occurs over here. Then to correct it, we first use these 2 ancilla qubits, or extra qubits, in order to perform what's called a parity measurement. So suppose that a bit flip occurs in the first qubit over here. Then we would use these two qubits to perform a parity measurement, which is basically a measurement on measures basically whether two adjacent qubits are the same or not. So by using these C naught gates, if we apply, for example, in this case, since it is 0, this would be switched to 1. But in this case, since this is 0, an operation would not occur, and this would be left in the 1 state. And for this case, this would be, of course, this would be applied. This would be set to, oh no, for the second answering qubit, this would be set to 1. And then an operator would occur. So our parity measurement would give us 1, 1. And for this qubit, our parity measurement would give us 1, 1, 1 as well. So for each different error, possible bit flip, single bit flip error, a unique parity measurement occurs. So if a bit flip occurred in the second qubit, we would instead get 1, 1, 0. So if you notice, these two bits are actually sufficient to encode basically all of the three different errors that can occur. So 0, 0 represents one error, 0, 1 represents a bit flip in the first qubit, this represents a bit flip error in the second qubit, and this represents a bit flip error in the third qubit. So by using these parity measurements, we can actually deduce which qubit was hit with the bit flip error, and we can use this information to perform a correction operation, in which we just simply apply the bit flip operator again. So in the case of a continuous bit flip error, in which this 0 state is instead converted into this state, and this 1 state is converted into this state, let's suppose that a continuous bit flip error occurs in the second qubit. Then we get this final state over here, and then we get this state over here. And so we get this final state over here with the parity measurements here and here. And so by measuring these parity measurements with a probability of 1 minus epsilon, we simply get this state over here, which doesn't need correcting. And probability epsilon, we get this state, this parity measurement over here, in which case we can simply apply the correction operators to obtain the original state. So with either outcome, it doesn't matter which outcome we get, we still manage to get the final corrected state. So it also works for continuous bit flip errors. Now, in the case of the 3-qubit phase flip code, in which we have a dephasing channel which applies a Pauli-Z operator. Of course, there's no classical equivalent to this, and since the classical channels, they don't have the property equivalent to phase. But in a quantum case, there's an easy way to turn the phase flip channel into a bit flip channel. And so we can use the same approach we use with the bit flip channel in order to correct the errors. So instead, let's suppose we work in the qubit basis over here by use of a Hadamard gate. Then the phase flip operator flips the plus state into the minus state, as with the bit flip operator flip the 0 state into the 1 state. So basically, for our dephasing channel, we would instead use this encoding instead of the 0, 0, 0 encoding. And then the procedure would basically be the same. We simply encode the physical states into the logical states by using this circuit over here. And notice how we've used these Hadamard gates at the end to convert the basis into the plus or minus basis. And so by the circuit is mostly the same, except we encompass our operations with the Hadamard gates to convert our basis from the zero basis into the plus basis. And so once we performed our encoding and we phase flip, we basically apply these to convert it into the equivalent bit flip form. We perform our correction and then we correct it again. And then we correct our final state. And so the Shor code combines the 3-qubit bit flip code and the 3-qubit phase flip code to simultaneously correct dephasing and bit flip errors at the same time. So in order to deal with dephasing errors, we first encode our qubit using the phase flip code over here. And then we encode each of these qubits over here using the bit flip code. And so this plus state is converted into this state in which we've replaced each of these physical states with their corresponding bit flip states over here. And so overall, this is the final state we obtain. And so the Shor code can detect and correct single qubit errors in general, because each single qubit error can be represented as in terms of their Pauli matrices, which in turn can be represented in terms of X and Z gates, and X and Z gates are basically bit flip and dephasing errors. And so by using this encoding over here, which can be achieved by this gate, this circuit over here, we can encode our physical states into logical states. And by using this recovery procedure, we can then correct our single qubit errors over here. And so the basic idea is by using the decomposition of single qubit operations into Pauli matrices, we can then combine our dephasing and bit flip error correcting codes into one concatenated code. And so that's all for today. And for anyone who's watched to the end of this lecture series, I thank you for your attention. But I want to stress that this is just the beginning. This is only touching the surface of quantum information theory. And so for those who are further interested, I encourage them to read the book, Nielsen and Chung, on quantum information, which is basically the book on which this entire lecture series is based. And in addition to this, of course, there is a plethora of different topics in quantum information that you can branch out through to from each of these different lecture videos. But I hope this lecture series managed to give you an adequate introduction into this exciting field of quantum information. Thank you for your attention.